It is the 1st of September 2025, approximately 9:20 a.m. And we're going to be getting into Dummett and Foote's section 1.7 on group actions. So, for the historical context, the concept of group action formalizes the idea of a group acting as symmetries on a set. It arose in the 19th century in the study of permutation representations of groups via Cayley's theorem. So group actions connect algebra to geometry, combinatorics, and number theory. They allow us to count orbits, study stabilizers, and understand the structures of groups via their interaction with other objects. Let's look at a definition. Let G be a group and X a set, a left group action, yeah, there's left and right, of G on X is a map. Is a map G cross X to X, from G cross X to X. So, looking at this element-wise, more element-wise, the Cartesian, coordinate Gx to G operated with X. And this satisfying Ex is equal to X for all, so that's your sort of identity looking thing, right? So for all X within the set X, 2 G H times X, well, operated with X, G operated with open parentheses H operating with X close parentheses for all GH within G and X within X. Clear enough? Well, of course not. Well, well, maybe. Maybe if you've seen this sort of thing before, or if you have some very gifted intuition of what exactly this implies. But we'll move on to discussing this more explicitly with more definitions and propositions to help us look exactly at what group actions are. So, another definition. For G within G, the map alpha sub G from X to X, that is the map, the function G of X equal to G operated with X is a permutation of X. The homomorphism V from G to S sub X is defined by G to alpha sub G is called the permutation representation associated with the action. This is a mouthful, but that works. Now we'll get into discussing orbits and stabilizers. So for x within set x, the orbit of x is g operated with x, which is equal to the set g operated with x such that g is within g. Well, I mean, we already have that x is within x, so I don't need to say that. So the stabilizer of x is stab sub g of x, which is equal to g within the group G, such that g operated with x is equal to x. Should just realize saying operator with is going to be a bit complicated whenever we get to operators, but for now we can hold that. So there we go, insofar as those definitions are concerned. That holds. Well, I mean, of course it is, it's a definition. But you know, and you can sort of see how intuitively this makes sense with namings. The orbit of something, it orbits around this. Stabilizing force of something, something that holds something else firm, such that that is the case. So let's move on to a proposition. And the proposition is this. Oops. Okay. That the stabilizer of x with respect to G is a subgroup of G. So, what's the proof of this? Well, what's a rough proof of this? If G and H are within the stabilizer of x, then G, then open parentheses, inverse of H, close parentheses, operated with x is equal to G operated with open parentheses, inverse of H, operated with x, close parentheses, is equal to G operated with x, which is equal to x. So, G inverse of H is within the stabilizer of x. Also, E operated with x is equal to x. So, E is within the stabilizer of x. Hence, the stabilizer of x is a subgroup of G. Now let's approach a major theorem, a definition, another proposition before getting into a few more calculative examples. So there's this thing, the orbiter stabilizer theorem. The orbit stabilizer theorem. Very important, because if the theorem has a name, other than just calling it theorem. No. So let G act on X and X be within the set X. Then the cardinality of G operated with X is equal to the class G such that we have the stabilizer of X. There's better words for that, but we're just going to stick to that for now. Which is equal to the quotient of the order of G over the stabilizer, the order of the stabilizers of X. The order of the stabilizer of X. Yes. So let's get into a proof of this. This is going to need a lot of calculative examples to better see. But let's look at a proof for now. So define phi to be the map from G to G operated with X by phi of G is equal to G operated with X. If G sub 1 operated with X is equal to G sub 2 operated with X, then open parentheses G sub 2, the inverse of G sub 2, G sub 1, close parentheses, operated with X is equal to X. So the inverse of G sub 2, G sub 1 is within stabilizer of X. So G sub 1 stabilizer of X is equal to G sub 2 stabilizer of X. Does that hold? Does that hold? Let's think about that. Yeah, that holds. So, there we go. Phi factors through the coset space. We haven't really discussed that in length, but just bear with me for now. G, we'll say divides. Well, divided by stabilizer of X, quotient G over stabilizer X, and induces a well-defined bijection. Such is the case with the quotient G over stabilizer of X mapping to G operated with X, G stabilizer of X to G, little g operated with X, elementally. Ergo, therefore, the order of G operating with X is equal to the order, the what is it? The yeah, I'm having trouble with this notational thing right here. Remembering exactly how to say that. G such that the stabilizer of X, class of that, where's that class? If G is finite, then G such that stabilizer of X is equal to the quotient order of G over the order of stabilizer of X. All right. Now let's get into some calculative examples. Which will either confirm our suspicions or debunk them wholeheartedly. It's the nature of such things. Well, actually, I think we need to do a definition and a proposition first. Yeah, transitive and faithful actions. So, an action of G on X is transitive. Okay, let's see. So this isn't. I don't like how they use transitive for both, transitivity and this case. But it's transitive in this case if G operating with X gives you big X, the set X, for some equivalently any X within the set X. All right, and a group action is faithful. Oops. If the associated homomorphism phi that maps G to S sub X is injective. That is to say, if the only element, yeah. This is similar to a property that we looked at earlier. Just missing it. Okay. If the only element acting trivially on X, the set X, is the identity. Okay, so let's see. Let me think about what that parallels, because something in my mind that is like it's an obvious parallel of something, but I'm not. See. there's a lot of things like that, right? I mean, maybe I was thinking about like how order divides under homomorphism. But I mean, this structure is a cool thing. Faithful if the associated homomorphism is injective if the only element acting through trivially on X is E. So it's faithful in respect to what? Group action if the associated. Well, suffice to say, let's just stick with this so far and then move on to proposition, which in this case is Cayley's theorem. So this says that every group, Cayley's theorem supposes that every group G is isomorphic to a subgroup of S sub G. Symmetric group. A subgroup of S. So let's roughly prove that. Let G act on itself via left multiplication. Which is why, the multiplication, like defining whether or not it's left, mentioning whether or not it's left or right is very important. Because you don't necessarily have it to be the case that everything is abelian. So you have to state directly which is it going to be, left or right. So in this case, left multiplication, G operated with x, G times x is equal to Gx. The associated map phi from G to S sub G, which is more elementally to say phi of G of x is equal to Gx is a homomorphism. If phi of G is equal to the identity, then G x is equal to x for all x within the group G. In particular, G is equal to the identity. Ergo, phi is injective. So we see that sort of similar structure. We can find this one thing, which is important by its nature, but also is equal to the identity. Ergo, we can say something is bijective. This pattern pops up over and over again, right? So, I mean, it's the nature of this type of proof, right? So there's probably something in proof theory that accounts for, like, here's the class of all of these sorts of proofs that are like this, but well, let's put that aside. So therefore, G is isomorphic to phi of G, which is a subgroup of S sub G, symmetric group. Yes, a symmetric group of G. I believe that's the way of saying it. Right. So now we can get into more calculated examples. Gotta check this. So let's look at the dihedral group action on vertices. So D sub 2n hedral group acts on the set of vertices of a regular n-gon by permutation. For n is equal to 4, D sub 8 acts transitively on the set containing 1, 2, 3, 4. Stabilizer of vertex 1 has size 2. The identity, that is to say, this is all to say, rather, the identity and the reflection fixing vertex 1. Yeah, stabilizer, right? It's fixing vertex 1. Identity and reflection fixing vertex 1. Okay, so orbit stabilizer gives orbit size 8 divided by 2, quotient 8 over 2, is equal to 4. Ergo, well, 4 which is equal to the number of vertices. Right. Now, let's move on to the next calculative example. So symmetric group action on subsets. S sub n, the symmetric group, acts on the set of k elements of k element subset, sorry, of 1 all the way up to n by permutation. This action is transitive. Why? Well, any k subset can be mapped to any other by a suitable permutation. Let's think about that. Right. Okay. Now let's go on to an example of something which is of a group action which is faithful. Something which is not faithful. My wife. Oh no. That's what I was thinking. Horrible. Horrible. Okay. Faithful action on integer sub n on the nth roots of unity. So let G be equal to Z sub n, which is equal to that generated by 1. I suppose additively, yeah. Define K, I think that's sigma? That's sigma? Big sigma? We'll just call it sigma, okay? It's equal to sigma to the k for sigma and nth root of unity. I should really just quiz myself on Greek alphabets until I can, like, you know, they're burned into my psyche. But that is what it is. This is a faithful action if k operated with sigma is equal to sigma for all sigma. Skibbity riz, man. Then sigma to the k minus 1 is equal to 1 for all primitive sigma. So n divides k minus 1, i.e. k corresponds to 1 modulo n. Very nice. And that's where we'll leave it for group actions with 1.7 and donut and foot for now.